Control, as I had explained previously, first thing that is there is, let's say you have any source, you have any load. Okay, in between what you need is a power converter. Okay, but power converter is nothing but it is having passive components and active switches. But you have to control, that is the main. Without control it is nothing. Just giving pulses to the switches and converter is operating in open loop will do nothing. So what you have to do is you have to control the converter. Now when it is an inverter, we control its voltage, frequency, this we control. When it is floating, means when it is independent of anything else, that I will explain. But when it is connected to some grid where frequency, voltage, or connected to anything where the things are defined, so what we do is we control the current delivered by the converter, and that comes where it is power control mode. Okay, active power, reactive power control mode. Now when you have an inverter, or let's say any converter, forget about inverter, DC-DC converter, any converter that you have, when it is a single converter, it's pretty easy. Okay, I should pretty easy with respect to the control that we are going to discuss today. So when it is, let's say a solar panel is there, then you have a converter and you are extracting power at MPP. So that time the control of the inverter, that control of the converter is just for MPPT control that you are doing if the output voltage is defined. But when it comes to microgrid, so microgrid is not a single source, it is having multiple sources. Second thing is the grid voltage has to be maintained. Third thing is there will be connection of this microgrid with the grid also. Maybe there will be utility grid, it might be connected to the utility. Most of the cases it is connected to the utility grid. Now microgrid could be AC or DC. Okay. Now the control that I am going to explain today is mostly on AC microgrid. DC microgrid is almost similar, but with respect to AC microgrid it is further simple. Okay, so you will understand why it is so. Now when let's say it's example why hierarchical control that we need, it's like, let's say you have a bakery shop. Okay, so when you have a bakery shop, only a person or two person, one is selling, another one is making bills, will do, right? Now when let's say you have multiple bakery shops in a city, then that simple management will not do. You have some upper level. Okay, so every bakery shop will have their own shopkeepers. On top of that, you need someone who is going to supervise all of them, right? Now if you have this bakery shop in multiple cities, then it becomes further up. So this is the hierarchy that we need to maintain in order to this is the hierarchy generally we maintain in the industry, and the same is implemented for the microgrid as well. So in microgrid, what we have, in microgrid we have a grid, we have load, and then we have multiple sources which is delivering power to the grid. Now that grid will be connected to utility grid, so we'll have a control at that level also. Okay, so one by one we'll come to that. So I kept this thing very simple so that at least hierarchical control you try to understand how it is implemented and what is the significance of hierarchical control in microgrid. Now hierarchical control structure is a flexible tool to manage dynamics as well as steady state performance of microgrid, including the economical aspects. Why I am saying economical aspect? I told you that it is connected to the grid. So how much power that you have to supply to the grid, or how much power, that is the power exchange to the grid that you have to look into. That looks after the planning and then economic aspects as well. Then what are the key roles in microgrid control? If it is a DC microgrid, it is only the DC grid voltage. But when it comes to AC microgrid, it is not only the voltage, it is voltage plus frequency as well as phase when it is there is a synchronization to the grid. Okay. Now we were first DC was invented, and then there were difficulties in DC because there was a problem in transmission. So we come to AC. We come to AC, but we come with n number of complexity in AC. Again, now we are moving towards DC, right? This DC microgrid is, I found there are literatures who are directly saying that DC microgrids are efficient than AC. Means if you operate in DC, it is efficient than when you are operating in AC. So that's why, so even if AC microgrids exist, so we need to look after whether it is, we have to control the voltage and frequency regulation that we need to keep in mind. So voltage and frequency regulation is necessary. Some person may think that why voltage and frequency when it is grid connected? When the microgrid is grid connected, why we need to think of frequency and voltage? Because it is defined by the grid itself. But thing is, the voltage and frequency of the converter which is connected to the grid, this voltage and frequency that will give you the output power. It is the voltage and frequency and phase that controls the current, and that finally controls the power delivered to the grid. As I told you, there will be multiple distributed energy resources. So there are many resources will be available in the microgrid. So there should be a coordination. How much power who will be generating, and it should not exceed their capacity, right? So there should be a coordination so that load can be shared according to their capacity, not equally. We cannot say equally we will share the load, because according to their capacity we will share the load. So see, resynchronization will be there, that it will take care. So as I told you, there will be a control of power exchange. There is a power exchange, active reactive power exchange with the grid. Active power is necessary, reactive power is for voltage control. From voltage control, the reactive power will come. Operating cost. So we need a control, not necessarily a hierarchical control, but it is found that this is one of the best suitable control method for microgrid control. Okay, there are 3 levels that I will tell you. So this is the microgrid. So we have multiple sources. We have multiple sources which need coordination and load sharing, and this is the microgrid, and there is the energy management in between, and then we have a hierarchical control for this microgrid. And we have shown the EV load as we have explained in previous lecture. Now there will be 3 layers. They say it is 4 layer, 0 layer, 1, 2 and 3. So we starting from primary layer, then we have secondary layer, then we have tertiary layer. So 3 layers that we are going to discuss. Here the innermost layer, that is the control which is doing this is as I presented that, which is the control of the microgrid. That is the primary control, that is the lowest level control, which will be doing all current control, voltage control, frequency control, everything that will be done by this primary control layer. Then we have secondary control on top of it, and then we have tertiary control. The fastest control loop will be the innermost control loop, which will take action as soon as possible. Then the upper control loop, when inner control loop settles down, then the secondary control will take action. Okay. If let's say, if primary control is not settled down and secondary control, let's say you have given a work to a person, as I told you, there will be multiple shops, okay, multiple bakery shop. One shopkeeper is already doing one work. You commanded him to sell, let's say, something, and he is in that process, and immediately you told him or her that, okay, you do this one. So he or she has not finished that work. Again, you have commanded for another work. It cannot be done. So you have to wait for that work to be finished, then only you can give the command. The same thing that happens here. Primary control has to be fast, okay. It can be slow as well, but if it is fast, then after it finishes fast, then secondary control will give second command. Is that fine? Okay, so the lowermost control, it is like, it is very simple. If you have gone through innermost current loop and outer voltage loop. Okay, so outer voltage loop generates the current reference, and current reference goes to the inner loop, and inner loop is faster, so that the gain of the inner loop is 1. That means what? Outer loop always sees that the inner loop is following the reference. Inner loop is following. So the secondary loop always sees that inner loop is working fine and I am ready to give the command. Similar for the tertiary loop, this is the slowest loop, slowest level, where it gives command to the secondary, and then secondary passes that command to the primary. Okay, so what is the role of the primary control layer? The role of the primary control layer is maintains voltage and frequency stability. So whatever frequency you want, whatever voltage you want, it is going to maintain. Okay, independent act. So these are the two contradicting things. I should not say contradicting, two different. When it is in islanded mode, there you need to define the voltage and frequency. When it is when it is active and reactive power sharing control, then there is when it is sharing with the grid, then it is connected to the grid, and your voltage and frequency is defined. You are doing the current control, and indirectly you are doing active and reactive power control. Indirectly you are doing the current control. So it is for both linear, independent of load, linear, non-linear, whatever, how load is varying, it doesn't matter, it will take care of it. Now there will be so it compensates secondary loop. So secondary loops supervise whether the command, it is the frequency and voltage command it is passing, whether it is following or not. Okay, if any deviation is there, that command will be passed to the primary loop, and it waits for the time by which it will track the. If your controllers are working fine, it will wait and it will see whether inner loop work has completed or not. Ensures electrical levels within the required values. So it will see whether references are tracking or not. So seamless connection and disconnection to the grid at this level it will look into. Okay. Now tertiary looks after this optimal operation economical aspect and manages power flow between grid and microgrid and main grid. Let's start with level 1 primary control. There are lot of tasks that it has to do. So first thing, as I already mentioned, that it has to stabilize the voltage and frequency, and let's say when this is our, if we see our utility grid, it's a immense, very huge utility grid, and you are taking power, or you are injecting power, is not going to affect much its frequency and voltage. When it is microgrid, if your demand and generation match is not there, there will be, if there is a mismatch, generator and consumed power, definitely there will be a frequency and voltage deviation will be there when it is in islanded mode. Okay, so it has to take care of that as well. So you can disconnect the DERs. Okay, properly share active reactive powers among the DERs, who is going to generate how much. And it is preferable that you should not have a communication. Without communication it is feasible. I will show you how it can be done. Without any communication, that yesterday I have shown you that for coordination we need a communication link. You can have communication link as well, but why not to have without communication link? Okay. Now whenever there is a parallel connection of anything, whether it is capacitor, whether it is a battery, whether it is power converter, there will be a circulating current will exist. It has to be. There will exist. So it will mitigate. Mitigate means it will not make zero. It will minimize it, the circulating current among the power converters. Also, it will take care of the DC link capacitor, which is one of the weakest link in a system. Okay, so it generates the voltage and current references. Okay, so everything that is implemented either, so this as I was telling you, so it can be either when it is grid connected, it will be in active power mode, power control mode, and when it is islanded, it will be in voltage control mode. So PQ control mode. Okay, so this I already told you that. So in PQ control mode, active and reactive power delivered from DERs are regulated to set references. Okay, so here what we are doing, we are controlling the active and reactive power. Here it is connected to the grid, the voltage and frequencies are defined. So what we are doing, we have the inverter which is going to, so we have, this is the voltage source converter, which is, so there will be an inductor here. Generally what we do is we control the inductor current. We control the inductor current in order to control the active and reactive power. Now here what we have, you can see here, we have the source, we have the inverter, we have the AC bus, and then there is a control loop. Here they are maintaining the DC bus voltage using a PI controller, and DC bus voltage, always you remember, always controlled by active power component. DC bus voltage is always controlled by active power component. What happens when there is a need for power? So immediately the DC link capacitor tries to discharge. When it tries to discharge, there will be a dip in the voltage. When there is a dip in the voltage, the controller understands that voltage is not maintained. That means there is a sudden requirement of power, and it tries to maintain the DC link voltage. The PI controller will adjust this active component of current so that active current is controlled. This is how the DC link voltage controls the active power flow. Now for reactive power flow, this reactive power reference comes from, here it is shown that reactive power reference is given, but generally it comes from voltage control. Okay, so voltage control, we'll see how it comes. So from here we are generating the reference voltage. This also will come reference voltage, and it is reference voltage is given to the voltage source converter, which is controlling the voltage, its frequency, its phase angle, and its magnitude at this point. After this there will be an inductor, so that there will be a control of current. So in this mode, if PQ control mode, the inverter is in current control mode. You always remember this. When the voltage is defined, you always work in current control mode. So as I told you that when it is PV and then we have a converter. So if the microgrid voltage is defined, so that converter will act in a power control or current control mode. Okay. So here also, since the voltage is defined at the AC bus, it is in grid connected mode. So therefore it will be in current control. This inverter will be in current control mode, in voltage control mode. Okay, in voltage control mode, this inverter will be in voltage control mode. Okay, so this AC bus voltage is now not defined. So it will define its voltage and frequency. So the microgrid is not in grid connected mode, it is in islanded mode or isolated mode, and its voltage and frequency has to be defined by this voltage source converter. So now the voltage source converter will act to generate a fixed voltage and frequency at this AC bus. It is the responsibility of this converter. So we have inner current control and outer voltage control. So reference voltage we are giving, according to which the AC bus voltage will be defined. Is that fine? So there are two modes. One is in PQ control mode, another one is voltage control mode. Both modes are in primary level 1, primary level. This both, when it is islanded mode and when it is grid connected mode, these two modes are controlled like this. So here generally what we do is we generally use droop characteristics. Okay, droop this droop characteristics, since we have this static converters, we are using this droop characteristics. I personally feel this droop characteristics is similar to, if power system people can confirm this, there is, I heard that, or I have seen during my BTech days, there is a device called governor in power plant, there is a governor which actually it's a ball kind of thing which rotates. When there is a lower in speed, that governor controls the steam flow, I think, and like that it controls the power flow. So same thing, power flow from different, if you have parallel connected generators, it controls like that. Roughly speaking, I think it is same concept that we have in droop control. Okay, let's see what is droop control thing. Okay, so droop control, one of the major advantage of droop control is if it is in master, there is, I told you that droop control is not the only method that you can follow. There are master slave framework also you can follow, but that needs sophisticated communication. If you are communication, then there is a separate field that you have to implement along with the control that you have. So that communication network is necessary for coordination, which is not required for droop control method. Droop control method allows power sharing without any communication. So how it can be done, that we'll see. So each source senses local demand and shares with others by adjusting terminal voltage, frequency, phase. That is for AC droop control, and for DC droop control it's much simpler, only voltage. Okay, so like this the information is actually indirectly communicating between the sources. So here is the droop characteristics for reactive power and active power. So active power is associated with frequency and reactive power is associated with voltage. So you can see here we have two units, everywhere we mention two units. So here you can see for DC subgrid, if you have DC and you have two sources, so then what will happen, based on how much is the voltage, you can see here for different voltage you have different power as well, but for same power you need to have different voltages. That is the droop characteristics. So for same power either you will have different voltages, or for same voltage you will have different powers. So according to, so based on how much power that you need from that source, accordingly the voltage of that source will be adjusted. Okay, or source or whatever is connected to the grid. In case of AC subgrid, you need two things. One is frequency, another one is voltage. Both are important. Now frequency is associated with active power. So for same frequency, it will generate a different active power because their droop characteristics or droop slope is different. And here reactive power, here at different voltage levels, different reactive powers will be generated. So this characteristics will be utilized for droop control. We'll see subsequent slides. Okay. Now when it is in islanded mode, so we need to generate the reference voltage. I will come to this. Okay, so droop control reduces circulating current among parallel connected sources. So it reduces, as I told you, we cannot make it zero, but it reduces the circulating current. So coordinated power flow, proportional power sharing among sources can be achieved using droop control. I remember during my PhD days, one student was working on parallel converters. He has compared this droop control method with master slave method. And when I was discussing with him, he was praising this droop control method like anything. That it is, first thing that he said, that it's very simple in implementation and very effective. Okay, when you go to industry always prefer what is simple, because industry says that industry needs reliability. So if it is simple, if it is reliable, then it is sustained, that it will be a sustainable product. It will sustain in the market. Okay. So droop control independent, autonomous and wireless control due to elimination of any communication link. So here in conventional droop control method, what it does is, so for AC grid, AC microgrid, so you need how much active power and how much reactive power that you need. First you need to know that. Based on that, for unit 1, how much will be the voltage, for unit 2, how much will be the voltage, for unit 1, how much will be the frequency, for unit 2, how much will be the frequency, that can be defined. So first thing that you need to know is how much is the frequency, how much is the active power and how much is the reactive power. So reactive powers are generated, then based on droop coefficients, these are called droop coefficient for active and reactive powers, and then it generates then it compensates the reference voltage and reference frequency, and it generates for that particular source, it generates the reference voltage. So here you are generating active and reactive power. Based on droop coefficient, you are generating how much deviation that you need for voltage, reference voltage and reference frequency. Then you get the reference voltage and frequency from which you generate the reference voltage for that VSC converter. Is that clear? Okay. Now let's see how this droop is implemented. Okay. Now there is so when it is connected to the grid, okay, when it is connected to the grid, so that grid voltage is defined, and then in order to control the power through this impedance, let's say this is one source, this is another source. This source you can control in your hand. This source is nothing but the utility grid whose voltage and frequency is defined. Okay, so it is fixed, it's infinite bus. Then this voltage you can control. Now you have in between one impedance you have, and then you are controlling the voltage difference across this impedance to control the current, and indirectly you are control the power flow, indirectly you are control the current. Now if you don't have this impedance, you need to have this impedance. I will tell you why, but before that let me tell you, this impedance may not be there, okay, but definitely there will be source impedances, definitely will be there, okay, that also will come into picture. But dedicatedly we need to put an impedance here. Why? Because this source is not a pure AC source, it's a PWM output from a voltage source converter, right? It's a PWM output. So the voltage here is something like this. So the voltage it is generating, this is the voltage. If it is PWM inverter, it is generating this 2-level inverter, 3-level inverter, it is generating voltage like this. This is this E at an angle of delta, and this voltage is, so this point voltage is this, okay. So this is converter voltage. Now this voltage is defined. So what is the voltage across this? This voltage minus this voltage. Now if this impedance is not there, then this voltage is a what? Pure sine wave, and this voltage is a PWM wave. It is not feasible. At the same time, the voltage at this point, PWM voltage at this point, pure sine wave, it is not possible. So you need, and that is from power electronics point of view. So you need, but from control point of view, you need an inductor here. You need an inductor at this point. Okay. Now so you need an inductor at this point. Okay, inductor is best suited. Inductor is best suited. Why? I will tell you. Okay. Now let's find the active and reactive power equations first. Then it will be much simplified to understand. Okay. So the voltage and current conjugate. You know why this current conjugate we take, right? Otherwise, this angle will not be negative. Okay, this, if you don't take this conjugate, then it will not, current angle will not be a conjugate. A current angle, this angle will not come negative. That is why this conjugate we take. Okay, then this equation comes, and then we separate out this one. Separate out this active power and reactive power equations. Now, why I told you this best suited if it is an inductor? What happens when it is a high power system, high voltage system? This definitely it is an inductor, because when high power, high voltage system, you need thick conductor. Okay, so thick conductors has much less resistance compared to inductance. So in that case, the theta becomes roughly. So if it is inductor, So this theta is 90 degree. This theta is 90 degree. Okay, that is the first thing. So if theta is 90 degree, so here we can say that this term becomes 0 and this term becomes cos theta. Cos 90 minus delta, so it becomes sin theta. This is fine. Then if it is 90 degree, this becomes 1 and this becomes cos. I think this should be sine. Then it becomes cos delta minus v square divided by z. Okay, so this is simplified. Now, I don't know how many of you know this. This delta value is very, very less. Okay, this delta value. What is delta? So let's say this voltage is this. This is the grid voltage. Okay, and this is the voltage that is converter voltage. This is the angle delta. Okay, so this voltage is Vcom and this is the E. This is E phasor. Okay, this angle is delta. This delta is nearly 0. It measures in radian. If this is nearly 0, so this becomes, so in next, so this becomes delta, sin delta becomes delta and this becomes 1. Okay, so now the Drude characteristics is, as already characteristics I have shown you, that omega is omega star minus dp p. So here so this frequency is depend on, so it's a straight line equation. So this is active power into the Drude coefficient, and then so this if we take, so here if we write, so F equals to F star minus some Drude coefficient into active power P. Okay, now when this active power P is 0, then it becomes F, frequency is F. So under, this is called frequency under no load condition. Similarly, voltage under no load condition. So that is what is presented here. So here you can see, so here the omega frequency is omega star dp, that Drude coefficient of active power, into P, and this E star voltage under no load, Drude coefficient under for Q, and this is the reactive power. So this is the voltage. So these are the for AC Drude. For AC Drude, these are the two equations. So here, that is why they mention that E star and omega star are DER output voltage and angular frequency at no load. When there is no active and reactive power delivered by this, when it is not delivering, so based on that, it is not delivering anything. So based on that their frequency and voltages are defined as no load, at no load. These are the Drude coefficient, and these are adjusted. Okay, so microgrid with DERs. If you have multiple DERs, distributed energy resources, then this should be satisfied. This should be, because this is what? This is omega equals to omega star minus delta omega. This term is called delta omega. How much? So actually what happens, if you know that our frequency, our grid frequency is 50 hertz. Our grid frequency is 50 hertz. But how much maximum and how much, so till how much we go from lower? What is the lower limit? What is the lower limit? No. Huh? Yes, 49.5 to 50.5. Okay, it has to be within that limit. Otherwise, there will be, if it is more, then there will stability issue may come. So here also you have to define some delta omega max, so that it should not. So if you have seen that as you are consuming more active power, the frequency is coming down, but there is some limit from no load to this. There should be a limit. We should not go beyond that. That is a design parameter and will be defined by you. So this is for each and every DERs. So this is dPn and dNn should be equals to this is delta omega star max, allowable frequency deviation. Okay, dPn is nothing but the active power droop coefficient of nth DER, and Pn is nominal power of that DER. Similarly, this is the maximum voltage deviation that we can allow for nth DER, and this is the droop coefficient. Okay, so voltage deviation. So this defines how much is the deviation that we can allow. Okay, when it is grid, that was in islanded mode. So we are defining voltage and frequency from droop characteristics. But when it is grid connected mode, so angular frequency and voltage are maintained by the grid. So only thing that we have to do is the active and reactive power references has to be generated, which can be done using these two equations. So reference is there, actual omega, and then droop coefficient if you can divide. If you know the droop coefficient, then you can generate the active power reference and reactive power reference. Okay. Now dynamic response. Okay, dynamic response. Now, if you linearize these two equations, if you linearize these two equations, this equation, so first we'll come with this active power equation. If you linearize it and use this droop characteristics, then what we can have is delta P, the change in active power, is equals to G into delta. So G is nothing but around this operating point where you are linearizing it. So around that operating point, G is defined as this, and then the delta is delta is the how much is the variation in the delta, how much variation that you need in the delta. So here when G is defined, so using this equation, so here using this equation, this is the small signal model for active power controls. So what it does is, how much is the active power deviation that you, how much is active power change in active power that you need, and then how much is the reference frequency, change in frequency. Okay, so what we have here is, from here using the droop coefficient, what we can have is here we are delta, we are generating so delta P multiplied G using, so this is the equation, that we are following. So delta omega star dP into delta P, then we get delta omega, this equation, and then if we integrate it, we will get delta. Okay, so here if you see delta is the angle, phase angle, and this is the change in frequency. By integrating it 1 by s, we can get delta, and G is nothing but delta P is nothing but G into delta. So these three equations are implemented here, where delta omega star is this delta omega star we can generate from here. Delta omega star we can generate from here. So delta omega equals to delta omega star minus dP into delta P. That equation is also there, this equation, and then using that we can generate the generate the delta P. So this is the transfer function. Here, if we adjust this dP, then time constant of this closed loop can be controlled, right? So during dynamic change in active power, so this is how we can control, by controlling the delta omega. So this is the variable that you have to control, by which you can control the active power. And this is only valid. One assumption was that assumption is very crucial, and sometime it becomes not valid as well. We have assumed that this is an inductor. That is valid for high voltage, high current application, where your impedance comprises mainly because of inductor and your resistance is low. If your resistance is high, this linearization may not be true, and that control loop may not work. And that is why this may not be very well suited for low voltage, low power microgrid, where your inductance, you cannot linearize like this. You cannot assume that theta equals to 90 degree and you can arrive this equation. Try to understand. Whatever we are implementing all depends on these two equations, and then we are linearizing those two equations only. So that is only possible when our assumption is theta is 90 degree, for Z is majorly, it is inductive in nature. Okay. Similarly, since this is for active power, similarly for reactive power also we can define H, and we can calculate the reactive power deviation as well. Okay. So here actually one small adjustment has to be done here, because it is dependent on, actually it is trying to, the voltage you are trying to correct, and voltage itself is varying. Okay. It depends on voltage, and voltage you are trying to control. So that is why an extra thing that you have to implement with an integral controller, so that it is called adjustable reactive power control. Previously that was not necessary, but also people implement for active power also, adjustable active power control also implement. There are literatures available. So here this reactive power, since it is dependent on voltage, it is implemented with that as well. Okay. Now what are the drawbacks of conventional Drup method? It is one variable dP. Okay, so impossible to satisfy more than one control objective. Okay, so active power control that you are doing, that is sufficient enough for it. So as I told you, assuming highly inductive impedance may not be true for low voltage transmission lines. Okay, this is one of the major drawback. So that is why people don't go with conventional Drup control method. They go for other modified method and all. Okay. Reactive power control may significantly affect voltage regulation. That is, as reactive power is directly affected by voltage, which I already showed you, that adjustable reactive power control that is to be done. Okay. Now unable to distinguish the load current between the load harmonic current and circulating current. So these modifications people have done, and also people have proposed many work on this, but I am explaining the conventional method in order to understand the base of that control loop. Okay. Secondary control. Now primary control I have explained, which is level 1. Now in level 2 control, so control at level 1 may cause frequency deviation in steady state. Okay, it may happen. Okay, if it is not there, fine, level 2 will be happy, but if it is not, then level 2 will try to correct it. Okay. So as I told you yesterday, this is done using storage devices. When there is a mismatch, the storage device comes into picture, and it will try to compensate whatever the active power compensation needs to be done. Okay, that is the role of storage devices. So storage device will come into picture, but definitely for longer duration it cannot do. It is for your home inverter, the inverter that you have at your home. It will run for 4 hours, 6 hours, not for 24 hours, 3 days, 4 days, like it is not possible. Then you have many batteries to be connected in series and parallel. So then it is more cost, and also you have to design the larger storage devices. Centralized controller compensates and restores voltage and frequency. This is what the level 2 control is. There will be a centralized controller will supervise and will try to compensate and rectify. So as I already explained, it has to be for stability, it has to be slower than inner loop to achieve decoupled dynamics of primary and the secondary control loops. Primary has to be settled down, then only the secondary control will come into effect. So it sets reference voltage and frequency for level 1 in grid connected based on power references, and in islanded mode based on individual voltage and frequency references. This operation, so it generates the voltage and frequency. So let's see how it can be done. So grid tied of voltage and frequency of main grid is the reference for grid connected mode. So here this is the secondary control. In secondary control, what we have, this is the to primary control. These things goes to primary control. What are these? Frequency and voltage. This frequency and voltage goes to. Now, if there is any deviation, so the frequency and voltage are set from the in secondary. This is the secondary control. This frequency and this comes from, I will show you what tertiary control is going to do. There are two modes. One is grid connected mode and another one is islanded mode. When it is islanded mode, it is predefined voltage and frequency. So that will take and it will pass to the primary control. So it is secondary control and this is the primary control. So when it is in islanded mode, these are the two references, voltage and frequency references, which will pass from here to the primary control, pass to the primary control. Now, if based on the references that is generated from tertiary control will generate voltage and frequency command, which will pass to the secondary control. Now, secondary control will see whether this voltage and frequency reference generated from primary, coming from primary, whether it is tracing whatever references it is passing from tertiary. So, from tertiary it is giving some references, and in secondary it will check whether under steady state this work is done or not. It will check. If it is not, it has its own controller which will control and try to track those two references in primary control loop. Okay, primary control loop will independently work. Let's say it is independently working and setting the references for voltage and frequency, and it is trying to track. Now, secondary control, what is the role of secondary control? It will see what references are set by tertiary control, it's above control. So it is taking from there and then it is passing to the lower level, and it is checking whether this is tracking whatever is commanded, whether it is tracking or not. If it is not tracking, it has its own controller, it will compensate, and then it will pass those references. It will update the reference for the primary control. Primary control has its own reference. Now, this will take references from tertiary level, and it will compare, and then it will set references for the primary control and let the primary control to track those references. This is the simple role of secondary control. Now, in tertiary control, what it does is, it is the last and the slowest control level. It considers the economic concerns for optimal operation. Actually, tertiary control is the main supervisory control. It looks after down the line, it will see that it's a black box. It will see only how much power it is delivered and how much power it's, means from grid point of view, it will see how much it is delivering to the grid, or there is how much is the power exchange between the grid and the black box. It will see. So it will see based on its optimal and economical concern. It will see whether this much power I should take or I should give or not. Accordingly, it will set the references and pass to the level 2. Now, level 2 will see whether the primary one is tracking this references or not. Okay, so it manages. So mainly this manages. It actually manages means it is the one which sets the reference power that is to be delivered, exchange with the main grid. In grid-tied mode, the power flow between microgrid and main grid can be managed by adjusting amplitude and frequency of DR voltages. That tertiary control doesn't understand. It only sets and passes it. Active and reactive power outputs are measured and then compared with corresponding reference value. Will show you to obtain frequency and voltage reference using separate controllers. Okay, so we'll see. So here what we have. So from grid, it measures the active and reactive power. It measures, and then it compares with its reference. It will set it what reference it has. It has its primary. It sets active power and reactive power references it has, and it will measure from the grid. If the grid active power, let's say active power is less in the grid, what it will do, what it should do, how finally what it will be done. Let's say active power is less. Active power is less. Okay. So what finally what parameters is going to be affected, and what parameter has to be adjusted by the level 1 control? Which parameter? The frequency parameter. Okay, the frequency reference it will, because the active power is adjusted by frequency, reactive power adjusted by voltage. It will see whether this is tracking or not. Using its own controller, it will generate references and it will pass to the level 2. So here this is what I have shown you. This is coming from primary. This is coming from tertiary control. Those references, power references. So power reference here, the actual powers and the reference powers are compared. Then their PI controller, it will generate reference frequency, reference voltage. This reference frequency, reference voltage will pass to this from tertiary control. It pass to this level 2. So reference frequency and reference voltage, and the secondary control will see this reference. It has no information about power. It has information about frequency and voltage. So it will see. So from primary control, it will sense what is the voltage and frequency. If primary is happy, primary is seeing that okay, I am tracing, he is happy. He doesn't know whether power reference is met or not. But secondary control will see whether it is meeting the required frequency and voltage or not in grid connected mode. If it is not, it will compensate. If it is, then it is fine. Then require active power is generated. So if it is met, then actually this will be 0. This 2 will be 0. Sorry, this 2 will be 0. Nothing will be there. This 2 also will be 0, because it is this active actual power and reference power are tracking. So this is how the 3 level of control is implemented for microgrid, and for control of active and reactive power exchange between the grid and the microgrid. So lower level is the fastest one, the upper one is the slower, then slowest one is the level 3 control. Okay, level 3 control based on active power and reactive power references. Based on it sets references, frequency and voltage for AC microgrid. It sets reference voltage and frequency for the lower level, which is level 2. Level 2 checks whether this voltage and frequency are set by tertiary control is tracked or not. If not, it has its own controller. It will set compensation frequency and voltage for level 1, and then it updates the level 1 voltage and frequency so that the actual voltage and frequency can be tracked. Okay, so this will be updated. This delta omega will be updated. Okay, so this is how 3 level of hierarchical control can be implemented for a microgrid in order to extract the required active and reactive power from the grid. Okay, so in conclusion, the robust control of microgrid in grid connected islanded modes of operation faces several challenges. Okay, as I told you, when it is single shop and you have one shopkeeper, it's fine. But when you have multiple shops, in multiple cities, then it becomes difficult, and you need this superior control. So I also proposed one work which one PhD student will work. where there will be microgrids with hierarchical control and they will communicate with each other. So when microgrids communicate with each other, then it is the upper level, the tertiary level where they communicate. So there is a communication link needed in between so that they can communicate about their active and reactive power demand at individual level. Okay, so accordingly they can fetch and they can deliver to the grid. So tertiary level control will communicate between the different microgrids. Hierarchical control structure suits best to mitigate most of these challenges. Levels are primary, secondary and tertiary control layers. Primary control with conventional loop control is explained, and challenges associated with loop control method is decoupling of active and reactive power control loop. This is a challenge. Also the challenge is when that challenge comes into picture when your assumption which is theta nearly 90 degrees is not true. Then this challenge becomes more prominent. Okay, level 2 and level 3 are the slower and slowest control loop respectively. So all are important, okay, but I personally feel level 1 does the most of the work. Level 2 and level 3 is the supervisory. They sets references for inner control loops. Okay, so here I will stop. So these are the references. There are good number of references available in the literature where you can see these things are further explained. Okay, what are the modification of these works which are done, those also are explained. I just give you the basic idea of this hierarchical control which will help you understand the modification of this control. Okay, so now the question answer session. So online, offline participants, if you have any questions from any point, let me know. I will be happy to explain.
Sir, it is the same like primary, secondary, and tertiary in the grids. Like the primary is primary governing system, secondary and tertiary. Like tertiary is market based, time secondary is both. AFC based, and primary is voltage and frequency control. Is same like that, sir, for the microgrid.
See, philosophy could be same. The philosophy could be same. The control wise it may be different based on system parameter. Every control that depends on system parameters. As I already mentioned, here one crucial assumption is theta equals to 90 degree, not equals to nearly 90 degree. This is one of the crucial assumption and may not be true for each and every system. Okay, as you saying in power system this assumption may be one of the best assumption that we can assume. For microgrid there could be a deviation. Okay, so philosophy could be same. We'll stop here. Thank you so much.